Hi again everyone, Chris Tisdell here. In this presentation I'm going to show you how to solve PDE via the method of characteristics. Now this video is a series on the subject of partial differential equations, PDEs. And this particular video may be thought of as an introduction to the method of characteristics. So we'll see why the method works and we'll do an example at the end. Now there's a famous conversation regarding the method of characteristics between a physicist and a mathematician. So the physicist, Dr. Smith at Stanford, says, "I'm afraid I don't understand the method of characteristics," when the method was suggested to solve a difficult problem. To which the mathematician John von Neumann replied, who's pictured here, "In mathematics, you don't understand things, you just get used to them." Now, despite what John von Neumann says, in this video we are going to understand the method of characteristics. John von Neumann is a hero of mine, but I think he's got it wrong here. We are going to understand the method of characteristics. Okay, so the method is known as the method of characteristics. It's a very powerful method and it relies on geometrical arguments and visualization. Now the method is very wide-ranging and it allows us to solve a range of problems, including linear, semi-linear and quasi-linear PDE. So here are some general forms. The first one is known as a linear first-order PDE. Then slightly more complicated, you've got the U dependency over here, semi-linear, and finally the quasi-linear, where you have the U dependence in the coefficients on the left-hand side as well. Now the nature of this video involves the semi-linear problem. So semi-linear includes linear, but not quasi-linear. Okay, so semi-linear problems are the focus of today's presentation. Okay, so here's our semi-linear problem. We're going to couple the problem with some sort of initial data or Cauchy data. And when you couple these two problems together, we refer to it as a semi-linear Cauchy problem. Now, as we've seen in previous videos, the solution to various Cauchy problems, for example, just a linear Cauchy problem, the solution can be pictured as a two-dimensional surface lying in three-dimensional space. So let's show how visualization and a bit of geometry can be used to solve this semi-linear Cauchy problem. Okay, so let's write the equation of the integral surface as the following. Now, when we call a surface that is a solution to the Cauchy problem an integral surface. And the idea behind the name is that integrations are used to solve these PDEs. Okay, now back up here, we've defined big F to be u of x, comma y minus u equals 0. Okay, now you might think, well, what's going on here? Think of the first u as a function of x and y and the third u as a variable. So together they sort of make up the arguments, if you like, or the variables of this big F function. Okay, so for example, if u of x comma y was x minus y squared, then big F would be x minus y squared minus u. Okay? All right. Now in particular, f equals 0 is a surface. That's the important part here. Okay, now essentially what we're going to do is we're going to take our differential equation and write it as a dot product. Okay, so if I take the f to the other side and sort of factor into a dot product form, then you'll see some nice things happen. Firstly, taking the f to the other side and factorising the left-hand side leaves 0 on the right-hand side. So you have a vector field over here dotted with this vector field over here is 0. So what can you say about these two vector fields then? Well, they've got to be normal or perpendicular, if you like, to each other at all points. Okay, now what about this vector here? This vector here is just the gradient vector from a third course in calculus, vector calculus. Okay, so geometrically we have the surface, big F equals 0. We know that the gradient from vector calculus enables us to calculate a normal vector, say n, to this surface. And it's given by this. You basically go to this expression here, you calculate the partial derivative with respect to x, with respect to y, and with respect to u, and you write it as a vector. Okay, so you'll get a -1 there in the third component. Okay, so now, and we know geometrically that this will be a normal vector to this surface. Okay, in particular, you see you've got a negative k component, so the vector will be downward pointing. Okay, because you've got a negative k. So here's our surface, here's our normal vector. Okay. Okay, so by normal vector, by the way, to a surface, we mean that the vector is normal to the tangent surface. Okay, to the tangent plane to the surface. Okay, so this is a normal vector, and this expression says that this vector field here is perpendicular or normal to this normal vector. Okay, so what does that mean? It means that if I define V to be this vector here, this vector and this vector are normal or perpendicular. Now, since this vector here is normal to the surface, what it means is that this vector here must be tangential, must lie in the tangent plane to this surface. Okay, so you've got this vector here, say, this is our vector V in this case, involving essentially these coefficients and this F. You know they're normal to each other. You know that this n is normal to the surface, and therefore the vector V must lie, it must be tangential to the surface, must lie in the tangent plane. Okay? So the vector V must lie in the tangent plane. Okay. So, remember, these things are just determined by the PDE itself. Okay? So, the PDE, the semi-linear PDE, provides a geometric requirement that any integral surface through a given point be tangent to this vector. Okay? So that means that if we start at some point of the initial condition, which must lie in that integral surface, and we move in the direction of the vector V, which we know from just looking at the coefficients on the right-hand side of the PDE, then we move along a curve that lies entirely within the surface, f equals 0. So think of maybe of a curve lying in the surface here. Okay? This curve is called a characteristic curve. Okay, so we know that we can describe, say, a curve, that green curve there, via parameterization. So you've got a curve that's lying in three-dimensional space. We can parameterize it using a vector function of one variable. In this case, the parameter would be t. Okay, so what we can do then is calculate a tangent vector to this green curve just by differentiating the components. Okay? So by the dashes, I mean, this is the vector p just derivative. Okay? So by x dash, I mean dx dt. So you can compute the derivatives of the components and you get a tangent vector. Now, because this curve lies in the surface big F equals 0, and this vector is a tangent vector to the curve, we know that the tangent vector must also lie in the tangent plane to the surface big F equals 0 at the given point. Okay? Now, since the characteristic is obtained by moving in the direction of the vector v, we conclude that this tangent vector and this vector v, which remember was defined down there, must be a multiple of each other, must be proportional. Okay, and that's really key to setting up the equations that we're going to use. Okay, so this vector is a multiple of this vector. Now, if you sort of equate the components, you can come up with 3 equations. And these are the most important equations I've introduced so far. This, okay, this, or just written in the compact differential form. You have these. Okay? So, essentially what we're going to do is solve these problems by building 2 differential equations, 2 ordinary differential equations, and then solving them. Okay? So if we, combine this and this, we'll get that, and this, we'll get that. Or you can combine these. Okay? So the solutions to the above pairs of ODEs will determine the so-called characteristics of the PDE. Okay, and they're going to be useful to help us build the solution. Let's actually have a look at an example and see how it all works in practice. Okay, so let's have a look at a problem and see how it all works. Here we're asked to solve the following Kosha problem for u as a function of x and y, where x is positive. Okay? So let's see how it all works in practice. Here we're asked to solve the following problem. Here, the PDE is a semilinear problem, and we have some Kosha data associated with it. Now notice that this isn't exactly the same style as the Kosha data that were in earlier slides, but this is still known as a Kosha problem. So basically along the line y equals x squared, the solution u is x. Okay, so let's return to our system of differential equations, if you like, set up 2 differential equations and solve them to form our characteristics, and then we'll look at building the solution to our problem. Okay, so this is a semilinear problem. Okay, and let's consider the following set of equations. Okay, so the coefficient of u sub x is x, so that's a, b would be y, and f would be the right-hand side. Okay, so what we need to do is form 2 ordinary derivatives, ODEs, out of these this set of equations. Okay, so let's form a dy dx type derivative out of this. Okay, so if I write that in the following, I get that. And if I team these two up, you can see that the x's are going to cancel out. So that's a nice simplification. So I can form something like the following. Yeah. Okay. Okay, so let's solve this one first. This is a separable first order ordinary differential equation. It's also linear. So that's why I'm going to solve it. So the coefficient of y is 1 on y, so it's going to be a constant times the integral of that coefficient. Okay, this is something you learn in a first course in ODE or a second course in calculus. X is positive, so when we integrate this we'll get logarithm. Don't need to worry about absolute value signs because x is positive. And I know that the exponential and the logarithm are sort of inverse operations. So I get the following. Y equals C1 x, where C1 is an arbitrary constant. Now I'm just going to isolate the constant. Okay, so now what? Let's go through and solve this second differential equation. Okay, so this is a separable differential equation. So if I separate the variables and integrate, I'll have something like the following. Okay, so I integrate both sides. Okay, so on the left-hand side, I'm going to get e to the u. On the right-hand side, I'll get something like x plus another constant. So you call it C2. Let's isolate the C2 here. Okay. All right. So what we're going to do now to build the general solution to our problem is that we're going to combine these two expressions through a functional relationship between these constants. Okay. Now you might ask, why should there be a functional relationship between C1 and C2? Well, C2 will, in general, depend on C1. Why is that so? Well, if you solve this differential equation to come up with this C1, many times what you have to do then is plug this expression back into your second differential equation. Now here we don't have any y's in this expression, so we're lucky. But if there were, for example, y's in this expression, you would have to substitute out the y for C1x. Okay? When you solve that differential equation, you'll get a new constant of integration, a C2, which will depend on C1. So C2 definitely depends on C1 in these problems. Okay, so we're going to combine our forms via C2 equals g of C1, where g is just an arbitrary but differentiable function. Okay, so C2's that, C1's that. We're going to have e to the u minus x equals g of y on x. So the general implicit type solution to this problem is the following. Okay, so you can kind of think of g here as an arbitrary function, and it kind of plays a similar role as a constant of integration does when you solve ordinary differential equations. Okay, but it's partial differential equations here, so g is more general. Okay, how do we find big G? Let's use the Cauchy data, the initial data. Okay, so So the initial data gives, okay, so when y equals x squared, u is x. Okay, so if I replace y with x squared in here and u with x, I'll get the following. So it'll be x squared on x, which is just x. So if I rearrange this, big G is going to be e to the x minus x. So let's put that back into here and replace x with y on x. So our final part of this solution will be the following. So we've determined a big G. Okay, so if you check this, you can show that this satisfies the Cauchy data and the original partial differential equation. Okay, so that's an example. So let's run through the ideas here. To solve the semilinear PDE via the method of characteristics, solve this system. You produce two ODEs. Luckily, these two, when you form an ODE out of these two, there's no u involved, so the equations uncouple, if you like. So you can come up with some expression like this. Now, if necessary, you might need to isolate the y or the x and then plug it in to either here or here, so you can solve these problems, okay? And out of that, you'll get another expression like this. Okay, you combine the two via a functional relationship. Now I've slightly abused the notation here because I wanted to cover both kind of aspects in the one go. So this is a very terse summary of the method here. Now just a little bit more on why there is a functional relationship between the constants. Hopefully, I mean I did say a little bit before about it in this problem. But remember that we're solving our ODEs along characteristic curves. And to get the value of u, we need to solve along every characteristic. And each time we solve it, we obtain the undetermined constant C2. Now C2 can vary between characteristics, but it must be the same along any particular characteristic curve. And the particular characteristic curve that we're considering is determined by the constant C1. So for example, for a certain C1, this would be a characteristic curve, and you would go through and get your C2. Okay? Hence, there must be a relationship between C2 and C1. And this is why you can combine like this. Okay? So that's the method of characteristics. I hope you found it interesting and useful. The best way to get good at these problems is just do lots and lots and lots of them. Now, like I said at the beginning, the method works on quasi-linear problems, although it's a little bit more involved. And we'll look at those techniques in other videos. I hope you can join me then.